Okay, this is going to be the video for Calc 3, section 15.6, which is the first section on triple integrals. And we will go ahead and jump in here. There's a lot to talk about here, so sorry about the length of this video, but we need to cover everything. All right, so what is a triple integral? We know that when we started out with calculus, we learned single variable integrals, right? So when we had a single integral, the idea was you had one output variable as a function of one input variable, right? That function could be represented by a curve, and you could find an integral which ended up being the area underneath that curve, so the sum of all the y's over some region of the domain. And the domain is one-dimensional, and so you're just adding up different y values essentially over a region. Also happens to represent the area under that curve, right? All right, so single variable is the summation. You can think of it as the summation of the output values. So it's the summation of these y values over the x. And it also has the interpretation of area. When we had a double integral, which we talked about in the first half of Calc 3, chapter 15 here, is we said now the domain would be two-dimensional, right? So the domain here is two-dimensional, right? And we still have a single output value for that, but we're summing those output values over this two-dimensional domain, right? So we're still summing output values, and we're summing a bunch of different output values that cover a two-dimensional surface, if you will. And since that's a summation of surfaces or values for z, in this case heights times areas, it really represents the volume underneath that surface in 3 dimensions. Okay, so what would a triple integral mean? Well, a triple integral means that we've gone from one variable in the domain to two variables in the domain to now three variables in the domain. And that means that the output variable is a fourth dimension. Okay, so we can't really draw anything here, and the integral no longer represents like an area or a volume. Okay, we have to use the entire three-dimensional space just to represent the domain. So just to represent the equivalence of having an area here or a distance here. And we have to use some other mechanism to even represent the output, right? So for example, let's say that that the output of this function, so we have something like, say, pressure, which is a function of x, y, and z. And maybe that's air pressure over x, y, z, which is three-dimensional space. So that these little numbers that I have written here are basically the output values for different x, y, z coordinates. So the entire three-dimensional space is the domain, and the output is some fourth variable that depends on all these other three input variables. All right. So then the triple integral is just going to be the summation of the total of all those output values, but over this particular three-dimensional region of the three-dimensional domain space. Just like you could think of the double integral as a summation of values on this surface, or a single variable or single integral as a summation of these y values over a region in the domain. Okay? Right, so it's important to recognize that the output is a fourth dimension, if you will, or a fourth variable, but the entire 3D space is, we're now working with the domain. So we've gone from a 1D domain to a 2D domain. Now we have a three-dimensional domain, okay? Now, when we covered the domain with one dimension, we just used dx, that was it. When we covered that with two dimensions, we could use dx dy, or we could use dy dx, or the area element could be r dr d theta if we switch to polar coordinates, okay? Now, to cover the domain, we have to have three variables, and therefore a three-dimensional volume element. So we have a volume element now, instead of an area element, instead of a length element. And that can be written in rectangular coordinates: dx dy dz, dx dz dy, dy dx dz, dy dz dx, and so on. There's actually 6 different orderings here that we could use. And if we use something other than rectangular coordinates, which we're going to start talking about later in the week and next week, there's other ways we can cover the dimensional space. But the volume element gets much more complicated. All right. So there's a lot of applications for triple integrals, at least as many as there are for double integrals in physics. You know how we talked about we had density and we had center of mass, and we could calculate center of mass if we had a thin lamina that was essentially two-dimensional. Well, now we can have a three-dimensional object, and calculate the center of mass. And the density could vary as a function of x, y, and z. We can calculate moments of physical 3D objects, like moments of inertia, or just the first moment, which allows us to calculate the center of mass. We talked about with two-dimensional integrals that we can calculate probability, like expected value, variance, skewness, kurtosis, things like that. And that's if you had probability related to two input variables. Well, now we can open this up to having three explanatory variables and then find the probability related to that. Okay, and then there's something called flux integrals, which we're going to talk about in chapter 16. That's the subject of our last chapter, which ties everything from the whole course together, which is called vector calculus. But in this section, we're going to focus just on how to evaluate a triple integral, one that has a three-dimensional domain, which can be quite tricky. And we'll see various things that can happen. The first thing we'll talk about is if we happen to have a rectangular region in the domain. So that corresponds to having a rectangular area for a two-dimensional integral. In 3 dimensions, if we have a three-dimensional box in the domain that we're integrating over, then we can employ Fubini's theorem again to say that you can change the order of integration to any order that you like. That changing the order does affect the limits of integration, just like it did for double integrals. Right? But it does mean that we can you can evaluate iteratively, starting with the innermost integral, and then taking the result of that, and then plugging that into the next level, and then taking that integral and finally evaluating the outermost. So we'll always work from the inner to the outer, right? And there are 6 possible orderings of these dx, dys, and dz's. And in some cases, some would be easier to evaluate, and some would be less easy. The thing that makes you choose would be the format of this. Right? The integrand, no longer, you can't really picture it as a surface anymore. It's the values of all the numbers of this 4th variable, right? But depending on the structure of this, it might be easiest to start with integrating x or integrating z. And so that would determine the orderings here. All right. Okay, so if there are dependencies, then you potentially have to integrate in a particular order. So we don't have to be restricted to just a rectangular area. We still integrate iteratively from the inside out, and you might have to have some dependencies here. So in 2D, we had a situation like this. Let's say that you wanted to do dx dy versus dy dx, right? Dx dy meant we would draw an arrow this way, and then we would potentially have a boundary that gives us the starting value and a boundary that gives us the ending value. And then that means that as we integrate in the x direction, these curves might be functions of y. And I realize at this point that there's a typo here. These should be y's, right? This should actually be x is some function of y, and this is x is some function of y. So if you're using the printed notes, please change that. This would be functions of y, because you can only have a function be or a boundary be a function of something that's further out in the integral. So since we haven't integrated y yet, these boundaries here can be functions of y. Okay, same thing here. If we were integrating in the y direction first, right, then we could have y as a function of x, and this typo again, it should be some function of x, and then this would be some function of x. Some function of x. So please make those changes in the notes. Okay, and then the outermost integral, right, would always be constants, because then finally you have to cover the entire shaded region over the last variable's limits. So what does that look like if we have a 3-dimensional area? Well, if we have a 3-dimensional area like this, we'll be picking a direction to integrate first. So let's say that I'm going to integrate in the z direction first. So imagine that we're crossing this area. So now the domain area is no longer a flat 2-dimensional surface. It's a 3-dimensional volume that we have to integrate over. But we're going to pick some inner integral first to start integrating over. And let's say we go in the z direction, right? We're going to imagine that we're going to integrate in that direction first, okay? What that means is that the starting and ending surfaces, they could be functions of both x and y. So these limits of integration here and here can be functions of x and y. And then when we integrate the next level up, if we happen to decide to do y first, then that means that these limits could still be functions of x. Right? On the other hand, if we decided to do z first, and integrate in this direction, right? Then these limits would be, these limits of integration could be functions of x and y, right? But if we decide to do x next, then these limits of integration could still be functions of y because we haven't integrated y yet. And finally, y would be a functional constant. So the point here is that any limit of integration can only be a function of variables that it has not yet encountered in our iterative integration. The textbook tries to break this down into different cases, like case 1, case 2, and case 3, and stuff like that. That's not really necessary to think about. If you just think about in general that anything inside can only be dependent upon something that's further away, further outside in the integral, then everything will work out. And we'll see examples of this as we go. Okay, best way to see this, as always, is to look at some specific examples. So we're going to take a triple integral, and we're going to actually evaluate it using all 6 of the rectangular orderings of dx, dy, dz, just to see how those would work and how they're different. Some of them we'll do by hand, some of them I've got written out here. Okay, so let's say we want to evaluate a triple integral over a 3-dimensional domain region E of the over the volume of some function. This function happens to be z, right? It's not that z is a surface, that it's just that the particular 4th dimension variable happens to be just the function w, let's say, equals z. Okay, and we're going to do this over a domain region which is a tetrahedron that's bounded by x equals 0, y equals 0, z equals 0, so the coordinate planes, and then the surface x plus y plus z equals 1, which is this kind of slanted surface that's cutting a piece of the first octant off. Okay, so when we evaluate a triple integral, typically we slightly alter the way we think about doing it compared to what we did in the 2-dimensional integral, but we know how to analyze 2-dimensional integrals. So what we do typically is we first ignore the inside integral. Okay, we pick 2 variables to evaluate on the outside. So for example, we could decide that we're going to do z on the inside. We've got our integrand here, and we're going to just use x and y out here. So first we pick the ordering, well, we pick a variable to be the inside. So in this case, I'm picking z, okay? And then we can decide what ordering we're going to do for the outer 2. So arbitrarily, let's say we're going to pick y and then x. So the outer 2 are x. So first we'll consider the outer 2 integrals. Okay, so the outer integrals are going to be something in the middle that we're ignoring for a second, dy dz. And that means that we have to first integrate a 2D, or we're going to eventually integrate a double integral that's going to be dy dx. Okay, so what you need to do is look at the 3-dimensional projection of the portion of the domain, this 3-dimensional shape here, and imagine that you're projecting it onto the xy plane. Okay, so imagine if you were shining a light down here, okay, on it like this, and it was the region that you're covering is casting a shadow down there. Okay, so it's casting a shadow down here on the xy plane. Okay, and then we will graph that as a portion of the domain over here. So I'm graphing like the shadow of the projection of the 3-dimensional portion of the domain, but down onto just the xy plane. Okay, now if we did that, we can see there's a triangular region here, right? And here's another sketch of it. It goes from 0 to 1, 0 to 1, and then there's a line here, right? This boundary right here is this line right here in 3D, okay? And then we just imagine that we're covering that like we're going to do a 2D integral. So if we decide to do y first, that means that we are going upward, right? And that means we start at the value y equals 0, and we end at the value of this curve, right? So this is a function curve, which is a line, which has a slope of -1 and a y-intercept of 1. So its function would be y equals negative x plus 1. And so that's why this limit of integration would be y equals 0 to y equals negative x plus 1. And then to cover the region in the other direction, which is x, right, we have to go from x equals 0 to x equals 1, which is why these boundaries are 0 and 1. So basically, at first, we ignore the inner integral, the third integral, and we just deal with the outer 2 integral, the outer double integral, right? And then we consider what happens if I now look at the inner integral. Okay, so let's go back to 3D. and imagine the inner integral. We know with inner integral, we're integrating with respect to z, okay? Here's my integrand here, okay? That's the function of the fourth dimension that we're integrating the value of, okay? But we have to establish the boundaries of integration. So how do we do that? So what you can do is go to the three-dimensional sketch, and now that we know that the outer integral is in the xy plane, imagine a person that's standing on the xy plane, right? And they're jumping through the volume that we're integrating. So they're jumping in this direction. They're jumping in the z direction, which is the variable of integration for the inside integral, the inner integral. And so then you can ask yourself the question, you know, where would that jumping start, right? And so that would start, I'm going to use red here, that would start at z equals 0, and it would end when they hit their head on this plane here. Actually, let me use a different color. That would end when they hit their head on this plane. So I'm going to need a function for this plane and the z value of that plane, right? So where would we stop? Where would we hit our head? Well, if the plane is x plus y plus z equals 1, then I can just solve that for z and say that we're gonna end. In other words, there's like an arrow here for the inner integral that ends at 1 minus x minus y. And that's why we have this limit of integration for the end and this limit of integration for the beginning. Okay, so just imagine a person standing on that plane jumping up. Where would they hit their head? And what's the equation in z solved for z? And that would determine the limits of integration. Okay, so now we set this whole thing up, and this is specific to the ordering z, then y, then x. We will integrate from the inside out iteratively, the same as we did with double integrals, but we'll start with the inside integral. So I didn't like write it out separately inside here. So what we're doing is doing this integral first. Okay, so we're treating z as a variable, and anything else, x and y, are both considered constants. If we happen to have an integrand that had x's and y's, we would just treat those as if they were numbers, like 3 or 5. So the antiderivative of z is 1/2 z squared, and then we're integrating from 0 to 1 minus x minus y. So we take our two copies and we plug in 1 minus x minus y in the left copy and 0 in the right copy. And the result of the inner integral is this, 1 minus x minus y quantity squared. So then we move out to the next level of integral. We're doing this integral now. We're integrating with respect to y. That means y is a variable, but if we encounter an x, we treat it temporarily as a constant, right? So since this is something squared, it would be appropriate to do this with a u substitution, with u being 1 minus y, x minus y. The derivative of that with respect to the variable, which is y, is going to be, the derivative is 0. The derivative here is 0 because that's a constant. And then for the y, it would be -1. So it's just going to be that du is -1 times dy, or du is negative dy. So we could substitute this in, and we would now have the integral of, well, actually, let me write it out here. We would have u squared, and the du would become, or sorry, the dy would become negative du. So, and then we have to change the limits of integration. So this was 0. So now u would be 1 minus x minus 0 for y, because we're plugging well, negative x plus 1 in for y here, right? So let's just be careful about that. Yeah, when we do the 0, we're plugging the 0 in for y. So we would now have, let's see, 1 minus x minus, and then for y, we would be plugging in 0, right? Make sure I've got that right. And then over here, we would have to plug in negative x plus 1 in for the y in the result, right? So this would be, the u would now be 1 minus x, and then for y, we have to plug in negative x plus y, okay? So I believe we end up getting that this is 1 minus x minus minus x. This ends up being 0 on the top, and this ends up being 1 minus x on the bottom. But because we have a negative, I employed the fact that if you pull the negative out, it inverts the order of operations, so, or the limits of integration. So this is 0 to negative x plus 1, but the negative of that result. So we conduct that integral using a u substitution, and we get a result. Okay. And if you carefully plug everything in and simplify, you'll end up getting this. And then finally, we conduct the outer integral, which now we're down to a single variable, so it's just regular integration. If you carefully plug everything in, you get 1 over 24. Okay. So, you know, some of these intermediate integrations will be easier and some harder depending on the order. But the main thing we wanted to show is how do you set this up, right? So the key idea is you pick something for the inner integral and the inner variable, and then at first you ignore it and you just deal with, okay, project onto the other plane, so the xy plane, the region you're covering, and then set up a double integral for the outer integral. And then go back and imagine if you're standing on that plane and you jump up and hit your head on something, right? What would establish the limits of integration in the inner integrals variable? Once you have the setup, you carefully integrate from the inside out, okay? And while you're integrating, you treat that one variable as the variable, and everything else is treated as if it was a constant. You may have to employ things like integration by substitution. Okay, so that would be the first of 6 ways we could order z, y, x. Let's take a look at the other 5 ways. Okay, so there's another ordering that projects onto the xy plane. That would be if we were doing z first, but instead of doing y then x like we did here, if we did x then y. Okay, so if we did x then y, at first we would ignore the inner z, and we would do xy, but we would integrate in x first. So we'd be moving in the red arrow this way. So that's going to be going from x equals 0 to, well, this is the equation y equals negative x plus 1. So I'm going to have to solve this for x. So I would get x equals, let's see, x equals negative y plus 1, right? Yeah. And so if I'm setting this up, I would say, okay, my outer integral is, I've got something for z, just ignoring it for a second, x and y. And we would go from x equals 0 to negative y plus 1. And then to cover the region in the y direction, we have to go from y equals 0 to y equals 1. So there's the outer 2 integrals set up. Then to set up the inner integral, we would go back to 3D. Imagine that you're a person standing on the xy plane, and then now we're going to integrate in the z direction, so you're jumping in this direction. Where would you hit your head? Well, you would hit your head on this surface, and solving this for z, again, we would get 1 minus x minus y. So finally, you would have integral from 0 to 1, 0 to negative y plus 1, and then the inner integral would be starting at z equals 0 and ending at z equals 1 minus x minus 1. You'd have your integrand, whatever it is, and then finally your final order. Okay, yeah, and let's go ahead and carefully do this one. I'm going to use the method where we kind of write out inner and so on. So the first integral, the inner integral, would be the integral from 0 to 1 minus x minus y of z dz. Right, z is the variable, so that means this is just 1/2 z squared evaluated from 0 to 1 minus x minus y. And so that would be one copy of something squared with 1 minus x minus y plugged in, minus another copy with 0 plugged in. And so we're going to end up getting 1/2 1 minus x minus y quantity squared. That's the result of the inner integration. Okay, then we would do the next level out, which in this case would be the x integral. So I'm just going to call this the x integral. And that's going to be integral from 0 to negative y plus 1 of, let me pull the 1/2 out, 1 minus x minus y squared dx, right? Which means we're treating the x as a variable, but the y is going to be considered a constant. Okay, I'm going to have to do, I think, some kind of a u substitution here, so let's do that. U is 1 minus x minus y. then du dx, because x is the variable, would be, that's a constant, so 0. This derivative is -1. The derivative of negative y is 0 because it's being held constant currently. And that means that du will be negative dx, or dx is negative du. All right. So let's do the substitution here. We have 1/2, and then we're going to substitute everything for u. So this becomes u squared. The dx becomes negative du, okay? And I need new limits of integration. So if I had 0, this is x equals 0. If x was 0, what would u be? U would be 1 minus 0 minus y. So u would be 1 minus y, okay? So when x is 0, this has to become 1 minus y, okay? And then when x is negative y plus 1, I can plug that in over here. It's going to be 1 minus, and for x, I'm plugging in negative y plus 1 minus y. That's going to end up being 1 plus y minus 1 minus y, which is just 0. So this is going to be 0, right? And then if I wanted to, I could pull this negative out, right, and swap the order to get this in a more standard form. You don't have to do that. You could retain the negative, right? Now, if I'm actually reversing these, then I'm gonna eliminate that negative, right? Taking the negative, if you swap the order of integration, because normally it's the integral b minus a, it would be the negative of a minus b. So by pulling out the negative, in fact, let me explicitly show that so I can show you what I mean here. I don't want there to be confusion. Okay. If I do this, I can write this as negative 1/2 integral 1 minus y to the 0 u squared du, which is equal to positive 1/2 integral from 0 to 1 minus y u squared du. And so that's going to be, the antiderivative is 1/3 u cubed from 0 to 1 minus y. And so we would have the two copies, 1/3 and then 1 minus y cubed. Actually, let me pull the 1/3 out too, so it becomes 1/6. So that would be 1/6, and then I just have 1 minus y cubed minus 0 cubed, or 1/6 1 minus y quantity cubed. Okay. And now we're ready to do the last integral. So the last integral was from 0 to 1 of dy. So I'll switch back to blue. So the dy integral is from 0 to 1 of the result, so 1/6 1 minus y cubed dy. This is also going to require u substitution. I mean, it's just negative, but just to be clear, I'll go ahead and do that. So u is 1 minus y, therefore du dy is -1, so du is negative dy. And so this is 1/6 integral u cubed. The dy is negative du. And then if u is 0, I'm sorry, if y is 0, then that means u will be 1 minus 0, which is 1. So this is the new limit of integration. And when y is 1, u will be 1 minus 1, or 0. Okay. So I'm going to do the same thing as I did up there. If I ignore the negative, I can reverse the limits of integration. U cubed du. So we have 1/6 times 1/4 u to the 4th, 0 to 1, which is 1/6 1/4 1 to the 4th minus 1/4 0 to the 4th. So it's just 1/6 times 1/4, or 1/24, which is the same thing we got with the first ordering, right? Okay, so far no real big difference there. We just slight variation in the details of the integration when we reversed the outer two x and y. But there's 4 more orderings, so we're going to go through those as well. Let's say that we wanted to use y and z as the outside, so we wanted to integrate in x first. So it's going to be dx, and then we can pick which way we want to go. Let's say we do y or z first on the last integral, and we finish with y. So if we arbitrarily decided to do that, at first we would ignore the inner integral, the x, and we would just deal with the z and the y. Okay, so in zy, you have to imagine that you're taking your region in the domain, this tetrahedron, and you're projecting it onto the xy plane. So imagine that you're projecting it onto the the yz plane, So imagine you're shining light in this direction, projecting it to form a shadow on the xz plane. That would form a triangular region here, which I'm sketching over here on the side. And then by deciding to do z first, we're picking the vertical direction, which means we're starting from z equals 0, and we're ending on this boundary, which if you carefully look at the line, it's just going to be a slope of -1 line with an intercept of +1. So z is -1 plus -y plus 1, which is why we're going from z is 0 to z is -y plus 1. Okay, that's how we establish that. And then finally, in the other direction, in the y direction, we have to cover from y equals 0 to y equals 1 to cover the entire shaded region, which is where we get the outermost constant integrals, limits of integration. Okay, now that's a little bit different when we consider the inner integral. Now we're talking about integrating in the x direction. So we have to imagine our person is standing on the yz plane in three-dimensional space, and they're jumping in the x direction. So where would they hit their head? Well, they would hit their head on this plane again, right? And that's the plane x plus y plus z equals 1. But because we're moving in the x direction, I have to solve it for x. So we're going to be going from x equals 0 to x equals 1 minus y minus z. That's how we establish the inner limits of integration. And then we would carefully go through the steps of evaluating from the inside out, and that will indeed evaluate to 1/24th if you want to try that. Okay. Okay, the fourth projection would have x on the inside, and we would use yz, but instead of going in the order z then y, we would go in the order y then z. So let's do at least the setup part of that. Okay, just so we can see. All right, so we would be projecting onto the yz plane, which means this is the region in the domain. Okay, so I would sketch that maybe. It's yz, and the region looks like this. And then I would pick the order of the direction for the outer two, which we decided to go y first. So when I'm building my integral, I've got something in the middle, but then I've got y first, then z. So I would do my usual go in the y direction. Let's see now in this direction, is that right? We did, we did up first last time. We did z first. This time we're doing y first, which means we're moving in the y direction first. So we have to go from y equals 0 to this boundary. Just kind of looking at this, it looks like it's z equals, let's see, negative y plus 1, y-intercept of 1, or z-intercept of 1 with a slope of -1, but I have to solve this for y, so it's going to be y equals negative z plus 1, right? Yep. Okay, so we're going to go from y equals 0 to y equals negative z plus 1. And then to cover in the outside region, we will go z 0 to 1. So there's the outer two integrals done. To do the inner integral, what I'm going to do is go back to my person here. Imagine I've got my my little person standing here, and they're jumping in this direction. So they're going to go from x equals 0 to x equals the plane. And so I would take this equation for the plane and solve it for x. So this is the final integral setup is going to have 0 to 1, 0 to negative z plus 1, and then in the integral on the inside, we're going to have x equals 0 to x is 1 minus y minus z. And then the integrand, and then our order, dx, dy, dz in this case. And we could carefully integrate that as well. All right. All right. Sometimes there's a particular ordering which is particularly nasty. Let's take a look at the last two just to kind of finish this. I think in this case, since everything is linear in planes, it doesn't really matter. They're all going to be roughly the same as far as difficulty in terms of integration or setting up. So the last one would be, let's see, what have we done first? We've done z as the inside. We've done x as the inside. So now we need to look at having y on the inside. So y on the inside. And then we could pick whichever one. If we decide to do z next, then we would have x on the outside. So we would start by projecting on the xz plane. So if you're projecting into the xz plane here, you're going to have this region there. That's a little harder when I graph this because things are going to look reversed. If I pick x here and z here, it doesn't really matter which. Yeah, it looks like we're going to have a line that kind of goes down like this again, right? There's the region. So I could do the setup, have something in the middle. We're going to do dz dx, and we'll make our 2D integral go in the z direction first, which means we have to go from z equals 0 to this line, which is z is negative x plus 1. So we're going to go from 0 to negative x plus 1 in the z direction. And then to cover this in the x direction, we have to go from x is 0 to x is 1. Okay, and then when we do the inside integral, we imagine that our little person is standing there and jumping up in this direction. So they're going from y equals 0 to y equals this boundary here. And if I solve this for y, it's 1 minus x minus z. So the final integral setup here would be 0 to 1 on the outside, 0 to negative x plus 1 on the middle, and then 0 to y equals 1 minus x minus z, integrand y, then z, then x, right? So that would be the setup. And then finally, the last one would be if we were doing y first, but we decided to do x, or y on the inside, we decided to do x next, and then the z finally at the end. Right, so we're projecting onto the xy plane. That means this is the domain for the outer two, the double integral. And if I were to sketch it down here, it would look like this. So see, it's kind of procedural. We're going to start setting things up. We have two things with something we're ignoring in the inside at first, dx, dz. And we would go in the x direction first. Let me label these x, z, because we're reserving y for the third one. We're going to go in the x direction first this time. So this is going to be from x equals 0 to this boundary, which is z is negative x plus 1, or x is negative z plus 1. And so we're going to go x from 0 to x is negative z plus 1. And then to cover the outermost one, we'll go z's from 0 to 1. All right, and then finally, to get the last one here, we'd imagine our little person standing in there, jumping in this direction, starting at y equals 0, ending at y equals 1 minus x minus z. So the final setup here would be 0 to 1, 0 to negative z plus 1, 0 to 1 minus x minus z, with an integrand in the order y, then x, then z. All right, so far, those are almost like, why would we do all six? Well, we wouldn't. We would pick one. But sometimes you have to integrate because, I mean, we just had a z here, right? But you could imagine if this was really complicated, maybe some particular ordering would allow you to do the integration and others would not, right? Or it could be that the region itself is more complicated than just planes, and that could cause issues. Okay, let's look at some other examples so we can see how these things work. Let's do this one. Evaluate the triple integral for the integrand x squared over the volume where t is the solid tetrahedron with vertices 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. All right, so if we were given it the problem this way, now this actually happens to be the same tetrahedron we're just looking at, but let's say we were just given the problem like this. What I would do is graph it, x, y, z, and sketch that. So I have 0, 0, 0, 0, 1, 0. Well, 1, 0, 0, 0, 1, 0, and 0, 0, 1. There's the tetrahedron. It happens to be the same tetrahedron, right? But in this case, we weren't given the equation of the surface for that plane. So could we come up with that equation, right? We know these other equations are the boundaries, x equals 0, y equals 0, z equals 0. But what's the equation of that surface if we aren't given it? Well, we could use procedures from earlier in the section. We could say, well, I know that I can make an equation of a plane with ax plus by plus cz equals n dot r0 if I have a normal vector, right? And I also know that you can find a normal vector for a plane by taking the cross product of any two vectors. Let's call them u and v, any two vectors that are in the plane, right? So maybe what I could do is I could make two vectors here. Like let's make a vector u and a vector v that join at the same point there. And then when I take u cross v, I'll get the normal vector to the plane, which will allow me to build the equation of the plane. So what would the u vector be? Well, the u vector would just be the difference between this point, which is 1, 0, 0, and this point, which is 0, 0, 1, right? So that would be a vector, let's see, end minus start, end minus start, end minus start. So that's the vector 1, 0, negative 1, right? And then this v vector here would go from 0, 0, 1 to 0, 1, 0, right? So we could add some complexity here by, not giving you equations of the surfaces in some way, right? So start, or n minus start, 0 minus 0 for x, 1 minus 0 for y, 0 minus 1 for z would be the vector 0, 1, negative 1, right? And then I could do a little cross product deal here to get the normal vector. That's going to be plus minus plus, plus minus plus, 1, 0, negative 1, 0, 1, negative 1, which would give me, let's see, the positive one would be 0 minus negative 1, and then the negative of negative 1 minus 0, and then 1 minus 0, which would give me 1, negative negative 1 is 1, 1. So the vector 1, 1, 1 is normal to this plane. And that means that to get the equation of the plane, I could say, all right, let's pick a point on the plane. Like, let's say, for example, it doesn't really matter which one I pick. How about let's pick this one. So my R0 will be 1, 0, 0. And then I could say, all right, then the plane equation is ax plus by, this is the a, b, and c over here, by plus cz equals n dot 0, or dot r0, which is 1 times 1 plus 1 times 0 plus 1 times 0, which is 1. And that's going to give me the equation x plus y plus z equals 1, which in the last example, we were given this in the problem. But if we weren't given this in the problem, we could solve it that way. Okay, so let me look at the problem again. And I'm just going to copy it down here. We're trying to evaluate this. And now I know what the equation of that surface is. It's that tetrahedron. In fact, I'll graph it again. And we'll tear off. But we'll only do this in one particular direction. So here's a sketch, again, of what we have. X, Y, Z. We now know we have this tetrahedron, right? And the equation of this surface is x plus y plus z equals 1. We went through that trouble to get that because they didn't give us that in the equation. But we want to integrate this value over that entire tetrahedral region in the domain. Okay, so we'll pick an ordering. I don't see any particular reason why we should pick one ordering over another. So let's just, let's arbitrarily go with this one. Let's go with zy, or yeah, let's go with So we got the integrand x squared. Let's go with zyx. Doesn't matter really, but let's just do that one just because I happen to have worked that one out in my notes. That way I can compare while we go. Okay. All right, so if we're going to set that up, we would first say we have the xy direction, which means I have to imagine I'm projecting this into the xy plane. And so I would sketch my domain in the xy plane. We would have this region here. And then I would pick a direction. When we set up, we're going to start by ignoring the inside and just doing dx dy. First in the y direction, which means we're choosing the arrow this way for the double integral. We're going from y equals 0 to y equals negative x plus 1, 0 to negative x plus 1. And then we're covering the x from x is 0 to x is 1. Okay, and then we can go back and imagine that our little person is standing there and jumping up and down. So they're going to jump from in the z direction from z equals 0 to z equals 1 minus x minus y. So you know what, I'm just going to add another variable, another outer, or actually this is on the inside. So we have 0 to 1, 0 to negative x plus 1, and then on the inside, 0 to 1 minus x minus y of the integrand, which is x squared, dz, dy, dx. So there's the setup. And now we'll start to integrate. So we'll start with the z one. That's integral from 0 to 1 minus x minus 1 of x squared dz. All right. So while we're dealing with z, x is considered a constant. So this is just, it comes outside of the integral. And we're just integrating 1 dz. So we have x squared. We just have z from 0 to 1 minus x minus y. And we're substituting this 0 and this 1 minus x minus y in for z. So I have my two copies here. Something minus something. And we're plugging in 1 minus x minus y in that copy and 0 in this copy. So it's going to be x squared 1 minus x minus y, right? So let me multiply that out. Now that's going to be x squared minus x cubed minus xy. Okay, let me switch colors and we'll do the next integral. The next integral is the y one, and it's going to be, so for the y integral, we're doing from 0 to negative x plus 1 of the result, x squared minus x cubed minus xy dy. And that means only y is an integral. So you can think of this as we have a constant, which is just x squared minus x cubed, integral of just 1 dy. And then I've got this term, which is minus, and the x is a constant, right? But this one has a y dy. So you could do all three terms separately, but I'm just going to do these together because it's just a constant times 1. And then, so you can think of this as a constant times 1 minus a constant times y, right? I'm doing those as separate integrals. All right, so let's do this left integral. We have our constant, x squared minus x cubed. And the integral of 1 is y, if the variable is y, from 0 to negative x plus 1, minus constant x. The integral of y is negative 1/2 y squared from 0 to negative x plus 1. All right. And so we've got our x squared minus x cubed, and we have two copies of these things. Right? We're going to plug in negative x plus 1 there, and we're going to plug in 0 there. And over here, I've got my two copies, 1/2 something squared minus 1/2 something squared, and we're going to be plugging in negative x plus 1 here and 0 here. Okay. And so, yeah, if you carefully multiply all this out, you multiply all this out, if you trust me, we end up getting 1/2 x to the 4th minus x cubed plus 1/2 x squared. You can verify that yourself. And then we have one final integral to do, which would be the dx integral from 0 to 1. So for the dx, we're going integral from 0 to 1 of this. So this is a standard single integral. You get, see, 1/2, 1/5 x to the 5th. And you know what, let me just do it all at once. It's going to be 1/2 and then 1/5 x to the 5th, 1/4 x to the 4th, and 1/2 times 1/3 x cubed, and all of that will be evaluated from 0 to 1. So when you take your copies and you plug 1 and 0 in, you can test and try this if you want. I got 1/60th when I was done. The main thing I want to worry about is the setup. Okay. Got a couple other ones. I know this video is getting quite long. Maybe I'll cut this off at this point and then do a part 2 for the second part. So in fact, let's stop for part 1 here, and then I'll do part 2 as a separate video.